Nothing about the Gila monster should exist. It is the only North American lizard with a venom arsenal more complex than most snakes, with 39 different proteins pumped from hidden glands in its lower jaw, flowing through grooved teeth and inflicting pain that can last for days. Experts still debate why evolution built such a slow-moving animal for pure biochemical warfare. So why did nature make a desert predator this extreme? Inside the Gila monster's venom glands, evolution has assembled a molecular cocktail, unlike anything else in the desert. This is not a simple poison. It is a collection of at least 39 different proteins and peptides, each with a distinct role in overwhelming prey or defending against threats. The star players are kallikrein-like serine proteases, enzymes that slice up proteins in living tissue, releasing bradykinin, a chemical that triggers intense pain and swelling almost instantly. Alongside them, phospholipase A2 breaks down cell membranes, fueling inflammation and tissue damage. Hyaluronidase, sometimes called the spreading factor, tears through connective tissue, allowing the venom to seep deeper and faster. Serotonin, better known for its role in mammal brains, acts here as a direct irritant, amplifying pain and causing blood vessels to dilate. This arsenal is more than just a list of toxins. Each molecule is carefully tuned for its job. Kallikreins drive the agony that makes a bite unforgettable. Phospholipase. O2 ensures that the damage keeps spreading even after the initial attack. Hyaluronidase opens the floodgates, turning a localized bite into a system-wide assault. Serotonin's presence intensifies every sensation, making the pain sharper, the swelling more dramatic. In some cases, other peptides like helodermin and gilatoxin can disrupt blood pressure or paralyze small prey, adding layers of complexity to the venom's effects. Comparing this to snake venom reveals both similarities and stark differences. Snake venoms often rely on a few dominant proteins, neurotoxins, hemotoxins, or cytotoxins, delivered in large doses through hollow fangs. The Gila monster's venom, by contrast, is a slow-acting blend, delivered in smaller amounts, but packed with a broader spectrum of biochemical tools. Proteomic surveys have identified 19 proteins in Gila venom that do not appear in any snake, highlighting just how specialized this lizard's arsenal has become. All of these molecules are stored in multi-lobed glands hidden in the lower jaw, ready for deployment. But even the most potent venom requires a way to reach its target. For the Gila monster, the next challenge is getting this molecular weaponry out of the gland and into the flesh of its prey, a task that demands a delivery system as unique as the venom itself. A Gila monster's mouth is a study in mechanical precision. Along the lower jaw, each tooth is lined with a deep longitudinal groove. No hollow fangs here, just open channels carved by evolution for one purpose: to move venom. The venom glands, hidden beneath the jaw, connect to these grooves by tiny ducts. When the lizard clamps down, pressure from the powerful jaws squeezes the glands, pushing venom through the ducts and onto the base of each grooved tooth. The process does not rely on a quick jab or a single strike. Instead, the Gila monster bites and holds, often for several minutes. It begins to chew, rocking its head and grinding its teeth deeper into flesh. With every movement, venom seeps from the tooth grooves into the wound, pulled along by capillary action. the same principle that draws ink up a paper towel. This is not an injection, but a slow, relentless flood. Micro-CT scans reveal the geometry of these grooves, narrow, millimeter-deep channels that run the length of each tooth, perfectly shaped to wick fluid from the base to the tip. The teeth themselves are fused to the inner side of the jawbone, a pleurodont arrangement that gives the bite extra grip, making it almost impossible for prey to shake free once the jaws have locked. Bite force measurements show that a Gila monster can generate up to 20 newtons of pressure, enough to drive the grooved teeth deep into tissue and keep them there. As the lizard chews, the grooves press against muscle and skin, maximizing the contact area and ensuring that venom is delivered over a wide surface. The longer the bite lasts, the more venom is transferred, and the more devastating the effect. Unlike snakes, which inject large volumes of venom in a split second, the Gila monster's method is all about endurance. The combination of jaw pressure, groove design, and persistent chewing transforms its mouth into a living syringe, one that delivers a complex chemical arsenal slowly but with devastating efficiency. This unique system is the reason a Gila monster bite is so memorable and so feared across the desert Southwest. A Gila monster moves with the patience of a stone, its thick body gliding over the sand, tongue flickering in and out. Every few steps, that dark forked tongue sweeps the air, collecting invisible chemical traces left behind by other animals. The Gila monster's sense of smell is its secret weapon. Unlike snakes that track with heat, this lizard is a master of chemosensory detection. Each tongue flick gathers scent molecules that are pressed against the Jacobson's organ hidden in the roof of its mouth, a structure tuned to decipher the faintest hints of life beneath the surface. Buried nests and eggs tucked under a crust of earth, the scent of a recent birth. These are the targets. The Gila monster can follow an odor trail across meters of desert, unerringly zeroing in on hidden caches. Field biologists have watched as a Gila monster stops abruptly, head swaying side to side, tongue working furiously. It pauses, then begins to dig, claws scraping through loose gravel and sand. Moments later, its snout breaks through into a rodent burrow or a shallow nest where eggs and helpless young lie defenseless. Despite its slow pace, the Gila monster's strike is decisive. Once prey is uncovered, the jaws snap shut with astonishing speed and force. There is no chase, no wasted energy. Instead, the lizard clamps down and holds, relying on its powerful bite and the arsenal in its mouth to finish the job. Its targets rarely have time to react. Young mammals, nestling birds, or reptile eggs, each offers a nutrient-rich meal, crucial in a landscape where food is scarce and unpredictable. This reliance on scent over speed is more than just a quirk. It's an adaptation shaped by the desert itself. The Gila monster's sluggish movements conserve energy, but its chemosensory precision means it almost never misses when it finally strikes. In a harsh environment where every calorie counts and every mistake carries a cost, the Gila monster's extraordinary nose gives it an edge. It is a predator that hunts with its tongue, a chemical tracker perfectly tuned for the silent drama unfolding beneath the desert's surface. A Gila monster's survival depends on a kind of budgeting most animals could never manage. In the harshest stretches of the Sonoran and Mojave deserts, food can vanish for months at a time. Yet these lizards endure, not by luck, but by turning their own bodies into living pantries. The secret is stored in the tail, a thick, blunt appendage that can swell with reserves until it makes up nearly 1/3 of the animal's total weight. When prey is plentiful, a Gila monster gorges, packing fat into specialized cells along the tail and lower body. This is not just extra padding, it is a carefully hoarded resource, a biochemical safety net that will be drawn upon when the desert goes quiet and the hunt yields nothing. Researchers tracking wild Gila monsters have documented fasts that stretch for 10 months or more. In laboratory studies, some individuals survive nearly a full year without a single meal, living off the energy stored in their tails. The lizard's metabolism slows to a crawl, burning through fat at a rate that would be impossible for a mammal or bird. Every movement is calculated. There is no sprinting, no chasing, just slow, deliberate steps and long periods of stillness, all designed to conserve energy. Even the act of hunting is measured, with ambushes replacing active pursuit. The physiology behind this endurance is remarkable. Fat storage in the tail can reach up to 30% of the animal's body mass. During lean months, enzymes break down these reserves, releasing energy gradually into the bloodstream. This process supports not only basic survival, breathing, heartbeat, muscle tone, but also occasional bursts of activity when opportunity knocks. If a nest of eggs is uncovered after weeks of scarcity, the Gila monster can still muster the strength to dig, strike, and feed, replenishing its stores for the next long wait. This adaptation is more than just a response to hunger. It is a form of evolutionary armor, shaped by a landscape where unpredictability is the only constant. The Gila monster's ability to fast for months, sometimes nearly a year, stands as one of the most extreme examples of energy management in any vertebrate. In the desert, where the line between feast and famine is razor thin, this slow-burning strategy is the difference between extinction and endurance. Across the parched landscapes of the Sonoran and Mojave deserts, the Gila monster moves in a suit of ancient armor. Each bead-like scale is more than a pattern. It is a shield grown from bone. Embedded within the skin, these osteoderms form a mosaic of hard, rounded nodules that cover the head, back, and tail, offering a defense that dates back to the age of dinosaurs. Unlike the smooth scales of other lizards, the Gila monster's skin feels almost pebbled to the touch, a texture that both deflects the bite of predators and guards against the abrasive grit of its desert home. Color is its second line of defense. Bands and blotches of pink, orange, and black coil across the body, with each individual wearing a unique combination. In some regions, the colors burn brighter. In others, they fade into earthy browns and rust. This palette is no accident. In the harsh glare of the desert sun, these warning colors broadcast a simple message: danger. Biologists call this aposematism, a visual signal that tells would-be attackers to think twice. Few animals in the desert are bold enough to ignore it. Even coyotes and raptors, notorious for their appetites, have learned to avoid the beaded lizard with its toxic reputation. The story of these defenses begins deep in evolutionary time. Fossil evidence and genetic studies place the Gila monster within the Toxicofera, a lineage of venomous reptiles that split from other lizards more than 100 million years ago. While most lizards shed their armor as they adapted to new habitats, the ancestors of Heloderma doubled down, evolving thicker osteoderms and brighter warning colors as the deserts of North America took shape. Over millions of years, The beaded skin and vibrant patterns became signatures of survival, warding off predators long before venom ever entered the picture. A timeline of Gila monster evolution reads like a record of desert history. Ancient relatives once roamed forests and floodplains, but as the climate dried and the land turned to sand, only those with the toughest armor and the boldest warnings endured. Today, the Gila monster stands as a living relic, a creature whose very skin records the battles of survival fought across epochs. Its defenses are not just adaptations, but echoes of a time when the rules of life and death were written in bone and color. A Gila monster bite is an event no one forgets. In the Arizona desert, a park ranger once reached for a stone, only to feel jaws clamp down on his hand. The pain was instant and overwhelming, described as fire racing up his arm. Within minutes, his fingers swelled and turned white, then numb. He could not pry the lizard loose. It held on for nearly 5 minutes, grinding its grooved teeth deeper. When the jaws finally released, the wound oozed blood and venom. The agony did not fade. Hours later, his arm throbbed with a relentless ache, and the swelling crept toward his elbow. For days, he struggled to move his hand. He spent a week in the hospital, doctors watching for signs of paralysis or airway swelling. There was no antivenom to give, only fluids, pain medication, in time. In Arizona, this scenario plays out only a handful of times each year, almost always after someone tries to handle or harass a Gila monster. The symptoms are always the same: searing pain, swelling that can double the size of a limb, numbness, and sometimes even temporary paralysis. Nausea, sweating, and low blood pressure can follow. In rare cases, swelling threatens to close the airway, turning a bite into a life-threatening emergency. Yet despite these dangers, no confirmed deaths have been reported in modern times. The lizard's reputation as a desert menace is built on fear, but the real risk comes from provocation, not chance encounters. For decades, the venom was seen only as a hazard, until a scientist named Dr. John Eng began to look closer. In the early 1990s, working in a modest lab at the Bronx Veterans Affairs Hospital, Eng isolated a peptide from Gila monster saliva. He called it Exendin-4, and its structure mimicked a hormone in the human body known as GLP-1. Unlike the natural hormone Venomous, Exendin-4 resisted breakdown, making it a powerful candidate for controlling blood sugar. Eng's discovery was met with skepticism at first. Funding was scarce, and few believed a deadly lizard could hold the key to a new medicine. But Eng persisted, eventually licensing the peptide to a small biotech company. In 2005, the Food and Drug Administration approved exenatide, marketed as Byetta, for type 2 diabetes. Millions of people now use drugs inspired by Gila monster venom. Exenatide helps the body release insulin, lowers blood sugar, and even aids weight loss. What began as a molecule for subduing prey has become a lifeline for humans, transforming lives far from the desert. The story of the Gila monster's venom is no longer just about danger. It is about the thin line between risk and reward, between fear and hope. The same chemical arsenal that can leave a hiker hospitalized now helps millions manage a chronic disease. In the Gila monster, nature's most unlikely predator has become an unexpected ally. Today, the Gila monster's venom, once feared, now helps treat diabetes for millions through drugs like exenatide. As habitat loss accelerates, the survival of this unlikely desert specialist grows uncertain. Nature's strangest designs still hold answers we have not imagined. Protecting them means protecting discoveries that could change our future. Share your thoughts below, or join us for more stories from nature's edge.